welcome back to this class of data science. And today, what I'm going to do, I'm finishing the I'm going to finish the tree classifier algorithm, and then probably I will have time to talk about tree regression, and there are some cool applications on that on restoring images. And so then we'll see how things go. If I have more time, I may start covering one more topic which is not in the syllabus, because I have been a little bit faster than I believe, but we'll see. Okay, so I'll start sharing the screen. Just a moment. Let me see. So this is.
Ecco. Buonasera, ciao.
Ciao, buonasera. Okay, so I hope you see my screen now. So.
Sì, vediamo.
Good. Okay, so we were talking about three classifiers, and so the idea is I quickly review what we did last week, and then also because to refresh your memory of the notations that we had. So the idea was that you have some training data, and let me see, where is my. Okay, so now I see my. Okay, good. Yeah, so you have some training data, and when we are talking about classifiers, you want to classify the data in different classes. So the training data has been classified by an expert, and so what you do is you have the data space. In this particular example, we think that you have a two-dimensional data space. You have two attributes, or so two coordinates in your data vectors. And so then you start asking questions whether the first attribute x1 is larger or smaller than s1. So s1 is here, the number. And so then you check that attribute, and if you are on the left, you go to one rectangle, and if you are on the right, you go to another rectangle. So then these rectangles are further divided by some values S2 or S3, and then you are dividing again your space. And so little by little, you are sort of filtering your data so that at the end, you know exactly in which rectangle you are. And so then this rectangle is classified to be, represent a class that you want to classify your X into. And so how do we do this this choice of the, okay, so here is my training set. So you have X's and you have their classes. And so the idea was that you divide your data space, the data rectangle, into smaller rectangles. And so once you have these rectangles, then you check what sort of training data you have in each one of those rectangles. And the training data is voting. And so in this particular example, if you look at this rectangle number 4, which has been divided in 4 rectangles. So now we have rectangles containing only one type of training data. And so now it's easy to say in which class you would classify your unknown X. So if you go through this tree structure, you end up in one of these 4. And so then depending on whether you have these red dots or these green squares, you classify your unknown X in one of those classes. So that's the idea. And so another question is, when we are doing these 3 algorithms, is how we build this splitting of the original data rectangle into these sub-rectangles. So that's the first question. So remember what we did last time. So we were looking at a particular rectangle R, and then nj is the number of data points that belong to that particular class in that rectangle. And so nr is the number of all data points in the rectangle. And so then we define pj to be the frequency of the jth class. And so you can take these pjs, which are frequencies, you can interpret them as probabilities if you like. So in frequentist probability, you can think that you pick one of the data points randomly, and then you ask what is the probability of that belonging to class J, and so the probability is Pj. So the sum of the Pj's is equal to 1. Okay, so then we use this picture of histograms here. So these Pj's are the heights of these columns. So you see that red here is the dominant class, and then we have blue and black classes which are smaller. And so if you need to classify a point using this rectangle, you would use the majority vote principle. So you look at what is the dominant class, which is the red one, and then you classify to the class red. If you do that, you have some misclassification error because some of the points were not classified correctly. The blue and black points are not classified correctly if you say that this rectangle represents red class. And so CR here is the winning class, okay? And so then we had the misclassification error. You take the heights of the other columns and you sum them up, or equivalent, you say that 1 minus the height of the winning probability is the misclassification error. And so if you have a pure rectangle, so there's only one class of data in it, then this MR is 0. Otherwise, it's something positive. We introduced the Gini index. This is important for us, which is measuring the impurity. So Gini index 0 means that you have a rectangle where there's only one type of data. Gini index positive means that there are other than one class of data, two. And so there's some misclassification error. So this is Gini index. And so then we, let me see, I go to, so here, so you have a rectangle, and we always split the rectangle in two, and I'm calling them the left and right rectangle. So I'm choosing one of the attributes J, and then I'm choosing a value S, and then I'm splitting my rectangle in two. So there is the left part where xj is smaller than S, and there's the right part where xj is larger than S. And so then we ask, what happens if I split the rectangle? What happens to the Gini index? And so we define this delta G to be the change in the purity. So the delta G is how much of the purity is increasing when you split. So you start with the original rectangle, and then you take the weighted Gini indices of the left and right rectangles, and the weights are how many points were classified to the left and how many points were classified to the right. So you use those as weights. And so then the question was, what happens to this Gini index when you split your R? And so delta G is measuring how much things change. We had a small theorem saying that no matter how you split your rectangle, you cannot go worse. So splitting is always a good idea because it improves the purity or decreases the impurity, decreases the Gini index. So it's always, it's never a bad idea to split a rectangle and use the sub-rectangles as classification because the impurity is lower. So this was a simple proof. I skipped that now because we had that already. And so now we go to the algorithm. So what we are doing is we are sort of moving sequentially. So we start with the initial rectangle. So we take a rectangle that contains all the training data. So you have the training data, it's in Rn. You choose the lower and upper bound for each interval in each direction, so that your rectangle, original rectangle, contains all data. Okay, so that's the starting point. And then you start splitting the rectangles. So you make the first split of the initial rectangle, and then you look at the resulting left and right rectangle, and then you split those. Then you continue, and so that way you are constructing a tree. And in order to do that, we need to have a criterion how we split the rectangles. And the idea is that we are trying to split the rectangles in such a way that the impurity is decreasing as much as possible. So that's sort of the optimal strategy. So let's start to look at the algorithmic part. So we define first of all leaves. So leaves are the rectangles that have no children. So if you have a rectangle in the tree and the rectangle is divided in two, we call these new rectangles as children of the original rectangle. Okay, so when you're moving in the tree, always when you come to a rectangle or a node, you have two possibilities, going left or going right. And those left and right, they're called children or offspring. So there are different names for them, children or offsprings. Now, if you have a rectangle which has no offsprings or no children, then we call it a leaf. So the tree has a root, that's the original rectangle, and it has leaves, which are the ones where you don't go any further. And now, if you look at those leaves, the leaves can be either pure, so that means that there is only one kind of data in that rectangle. And in that case, we say that the leaf is a pure leaf, and we collect the pure leaves in a set which is called RP. And the leaves that are not pure, which contain more than one class of data, they're called mixed leaves. And so Gini index in that case is positive. So checking the Gini index of a leaf, you realize whether this rectangle is pure or mixed. And so this is the starting point. So here is the tree growth algorithm in few words. So what we do, we start with R0. So this is the original rectangle that contains all the data. And of course, we assume that in our original data, you have some impurity, because if you don't, so then there's nothing to classify really, right? So if everything is already in one and on one only class, so then we don't have any reason to classify anything. So the data has to have some impurity, and so therefore the Gini index is positive. Okay. So now what do we do? So we have no pure leaves, because now our tree is so-called trivial tree. We have only one single rectangle. So the set of pure leaves is an empty set, so there's no pure leaves. And the mixed leaves, well, we have just one rectangle, so we have just one leaf. In this case, the root R0 is at the same time a leaf of the tree. So we have like a seed, a trivial tree. And so then we continue repeating the following steps. So as long as you have mixed leaves, so as long as Rm is non-zero set, a non-empty set, you pick one of the rectangles from your mixed leaves. For instance, the first one. So you can think that these are the mixed leaves are in some order. So you just pick one of them, and you remove that leaf from the set of mixed leaves. Why do you remove it? Because you're going to split it, and when you split it, it's no longer a leaf after the split, because then it has two offsprings. Okay, so therefore you have to remove it from the mixed leaves. Then you split it in an optimal manner. So you say that your R, which you picked, is divided in two rectangles, and you are trying to do this optimal splitting in such a way that the split maximizes delta G. So it maximizes the improvement of the purity, or has the maximum effect on the Gini index. So delta G is what you look at, and you choose the split in such a way that delta G is maximized. And then you check your left and right leaves. And so these RL and RR, they are now leaves because you just created them, and they don't have offsprings yet. So now you check if they are pure leaves or mixed leaves, and according to which one they are, you place them either to RP if they are pure, or RM if they are mixed. And so you removed one mixed leaf and you created two leaves, and the leaves can be either pure or mixed, and so then you continue. Okay, so this is the algorithm. Now, do we know that this converges? The answer is yes, because the data is finite. So you can only split the rectangles a finite number of times. And at the end, at worst, you have leaves that contain just one data point. Probably you have more data points in each leaf, but so you can you see that the maximum number of possible leaves cannot exceed the number of data points. And since the data is finite, you know that the tree that you get by this algorithm is going to be finite, and the algorithm stops at some point. So this is definitely a converging algorithm. There's a stopping criterion there. It may not be the most effective algorithm in the world, but it is certainly something that converges. So let's look at what this optimal splitting means. So I said that this optimal splitting means that you're maximizing delta G. And I realized that this slide and a couple of other slides are not in the slides that I uploaded, and I will re-upload the new version after my lecture. So you will have also these. There are maybe three or four slides that are missing from the one that I uploaded. Okay, so we have the rectangle R, and so we are splitting it into the left and the right offspring. Okay, so the left offspring is, so you choose, if you have an index J, remember you can choose this J in many ways, and you can choose this S in many ways. So suppose you have one J, J equals 1, for instance, and then you choose a value S. So you are splitting your rectangle into using J and S. And then you look at the change in the Gini index. Now the change in the Gini index depends on J and S. Okay, so this is how much the purity is improved when you split using the J attribute and value S. What is the optimal splitting? Optimal splitting means that you are choosing the J and the S that maximizes the change in the Gini index. So that's the definition of optimal splitting. And this again is it may not be unique. So you may have several splits that are producing the same change in the Gini index. So in case you have several, you just pick one, let's say randomly. But the idea is that you always can find at least one optimal splitting. And so what does this mean? So you're trying to find the attribute J and the split value S so that the change in the purity is maximum. Okay, so this is the algorithm. So now you can ask, is this a complicated optimization algorithm? It could be. So it's so how we are doing it here is simply an exhaustive search. And I will come back to this later. So if your data set is large, this may be not the optimal way to do that. But so let me explain how you do it if you have a moderate size of data set. So here is a picture. So I have plotted here a two-dimensional rectangle where I have points x1, x2, etc. And what I have done here, I have chosen one attribute, which is in this case the first component, and then I am sorting my data so that when you project these data points to the first attribute axis, the x's are in increasing order. So the first component of x1 is less or equal to the first component of x2 is less or equal to the first component of x3, etc. And so I go through all the data points. And what in this picture you will see, what I do, I always choose the values sigma so that they are in between the values, halfway the values of adjacent xj. So here notice that x2 and x3, they have the same value. So what I need to do is when I have two data points which have exactly the same value for the j attribute, I'm just deleting one of the data points so that I don't have a replication of the value. Okay, so here is a little bit more, let's say, mathematical explanation, and we can go back to the explanation. So first of all, we take the data and we are sorting the data points according to the jth component so that they are in increasing order. And what I have forgotten to say here is that you remove from this list of values, you remove the values that are repeated. Okay, so if you have x1 and x2 having the same component, you are just removing that value so that each value is only given once, because we are really interested only on these values of the attributes, not how many times they are being represented by the data. And so then we choose these sigma L's to be in between the values of adjacent points xl and xl plus 1. And so you have finitely many of these. Now, what we do here, we do an exhaustive search. We calculate for this particular j, we calculate the change in the Gini index for each value sigma L. So we are using this sigma L as a split value. And we are calculating how much the Gini index is decreasing when we use the sigma L as a split point. And now we have a finite number of values. We are choosing the value Sj that is giving the maximum change in this Gini index. So you have a finite number of values, you just pick the one which gives the maximum. If you have several maxima, you just choose one of them, for instance, randomly. Now you have these Sj's for each attribute. Okay, so here I fixed attributes and I calculated the Sj for every attribute. And so then you go through all attributes and you pick the attributes for which this Gini index change is largest possible. And so there's an outer loop now. So the inner loop is that you're skimming through the split values, and then you're skimming through the attributes. And so then you get the optimal split direction and the optimal split value, J star and S star. So as I said, this algorithm can be heavy if you have lots of data points and if your dimensionality is high. And so in those cases, you may want to do something. And so one of the things that you can do is that you use subsamples of your data. And I'll address that question later. But so at this point, we are thinking that this is sort of a viable way to do that. So, okay, so skim through all the possible split values, skim through all the possible attribute values, choose the one which gives you the maximum change in the Gini index, and that's the optimal split. And so here are some observations. So first of all, since our data are finite, so we have only finite number of data points, the algorithm converges to a tree whose leaves are all pure. Remember, the stopping criterion was that you continue the splitting until the set of mixed leaves is empty. So that means that at the end you have only pure leaves. And so each leaf contains data points that are belonging just to one single class. So there's no ambiguity when you are using that tree for classification. And so this tree that you get using this algorithm is called a maximal classification tree. It's called Tmax. So that's a large, possibly really large tree. And so it may be very heavy to use. Now in practice, so this Tmax may be so large that it is, first of all, it may be a burden to use such a tree for classification because it's such a large tree, but it may also have the tendency to misclassify. And why is that? Because you're using the training data, and the training data is, of course, as any data, is possibly noisy. So there may be some errors in the attribute values. There may be also errors in the classification. And so this Tmax is tailored to specifically classify the training data. And so suppose you have, let's say, 2 points which are very close to each other, and they are classified in 2 different classes. So the tree algorithm is going to eventually separate those 2 points in 2 different leaves. But now if you think that these values that you're looking at are noisy, it is very easy to imagine that a different noise would, you know, classify them differently, in the sense that what was on the left becomes something which is on the right, and vice versa. So a little noise in data may change where you classify one single point, and so therefore the maximal tree is sort of prone to misclassify because of noise in the data. And so therefore, for these 2 reasons, you don't want to use the maximal tree usually for classification, but you want to use a tree which is, let's say, smaller, and its leaves may not be pure, but it does a decent job. So that's the idea. So we want to find a smaller tree where the leaves may not be pure. The classification is done by majority vote principle. So when you arrive to a leaf, you just check what is the most what is the dominant class, and then you use that for classification. So there may be some misclassification error even with your training data, but at least the tree is a little bit smaller and it's not that prone for noise in the training data. And so how do we do that? So there are basically 2 possibilities. Either you stop the growing of the tree at some point. You decide, okay, so this is complicated enough. I won't create a tree that has, let's say, more than 200 leaves. So that's one possibility. The other recommended way to do is that you grow first the maximal tree, and then you do what is known as pruning. So you start cutting branches from your tree so that you get a smaller tree. And so here is first of all a question. So should we stop growing the tree before it is too large? So this was the first idea that I said. So maybe you don't want to grow a maximal tree. You want to grow just a large enough tree. But so then if you do that, you need to have a criterion when you stop, like, growing the tree. And one natural idea would be that if you don't gain anything, so if your change in the Gini index is basically 0 or less than some threshold, so maybe you don't want to split any longer the rectangles. So that's an idea. This idea has proven not to be such a good idea, because if you look at this picture that we had before, so if you look at the first split here, so let me point out that the split that I'm doing here may not be the optimal split, but I'm just, this is sort of a some sort of worst case scenario picture. So suppose that your first split would be from this rectangle 1 to rectangle 2. Now, if you look at the change in the Gini index from 1 to 2, and if you do the calculation, you see that the impurity is not changing at all. So delta G from 1 to 2 is 0. So why is that? Because if you look at the impurity of rectangle number 1, exactly 1/2 of points are in red, and exactly 1/2 is in green. Okay, so the impurity is maximal here. If you go to this rectangle 2, which has been split, and you look at the subrectangles, the subrectangles have the same property. So the impurity is maximal in both of them. So we have equally many red and green dots in both subrectangles. So that tells me that the impurity has not decreased at all when I moved from 1 to 2. And so if I would use the criterion, the stopping criterion, that I stop when the delta G is not changing, what I would do then is I would stop at tree number 2. However, if you look at the subsequent splits, we go to 3 and 4, you see that the subsequent splits are making all the leaves pure. And so this is an example where one split may not help you at all, but the splits that come after are doing a perfect job here. And so therefore, this is sort of the example that one should bear in mind, so that this criterion that delta G at one point is small or 0 does not necessarily mean that you cannot gain anything afterwards. So you can gain a lot afterwards, and so therefore the strategy that you stop when delta G is less than some delta G is less than some threshold is not usually advocated. So it is not considered to be a good idea. Okay, so we need to do something else, and so the something else is pruning a tree. So the recommended procedure is that you first of all you construct this maximal tree. So this is step 1. So you construct the classification tree with terminal rectangles or leaves that have vanishing impurity index. So you go all the way to the maximal tree, and then you start pruning. So you start cutting branches from your big tree in a way that you are sort of trying to balance between the impurity of the leaves and the classification quality of the tree, while at the same time simplifying the tree as much as possible. So you try to decrease the so-called complexity. So we'd have to define that complexity, and I will come to that definition soon. But so you have 2 things to look at. Cost means how much misclassification your tree is making with the training data, and complexity, how large your tree basically is. And so we are balancing between those 2. So this is a typical objective in optimization and in, let's say, in inverse problems, for instance. So you always are balancing between different objectives that you may have, which are conflicting. And so let's look at the how we define that, the objective function that we are looking at when we are doing the pruning. So I said there is the cost, so misclassification. So we are going to use the misclassification rate or misclassification error, as we defined it earlier, as a criterion of how much we want to prune a tree and still consider it to be a good classifier tree. So remember, if you have a rectangle R, when we are using the majority vote principle, we denote by CR the class that represents the majority of R. And majority is not, majority of, so maybe this majority is not the good word, because the winning class may not be the majority if you have several classes. If you have 2 classes, the winning class is also the majority class. But if you have 3 classes, you may have the situation that one class has the biggest representation, while the other 2 classes together may represent the majority. However, when we say majority vote, we mean that we classify with the rectangle to the class which has most members of all classes in that rectangle. So Pj, remember, is the frequency of the jth class in the rectangle. So we are choosing the j for which Pj is the largest. So remember this histogram: red, black, and blue. So CR would be the red class because that has the most members in the rectangle. And so all the points which are not in the winning class, they are misclassified. And so therefore the misclassification rate is, we are asking how many let's say percentage-wise or ratio-wise, all the points are misclassified. So how many points do you have in the classes which are not the winning class divided by the total number of points in that rectangle? So this R here is a number between 0 and 1. So that's the misclassification rate. If you have a pure leaf, misclassification rate is 0. And so this R can be large, close to 1, if you have lots of classes, and the winning class has a narrow margin to be the best class. But so R is always between 0 and 1. Okay, so that's the number that we are going to use to define the cost. And cost means here the cost of misclassifying. Okay, so that's my first concept. The second is the complexity of the tree. So we want to find a measure for so let me finish this cost part first. I jumped a little bit ahead. So if you have a tree T, so we define by L. I denote by L the leaves of the tree. So L is the set of all the leaves. Okay, so this is my L, and so now we can define what is known as the relative weight of the leaf, and the relative weight of the leaf is you take the original data set where you had P data points. So P is the total number of data points. R is a leaf. And so now you're asking what percentage of all data points belong to the rectangle that is this leaf R. And so NR is the points in the leaf, and P is the total number of points in your data set. And so nu R is the weight of the leaf, meaning how many points ended up in this leaf. So the sum of these nus is equal to 1 because every data point ended up in one of the leaves. And the weight is how many points you have in each leaf. So this is an important concept. And so then, so remember, P is the number of data points in the training sample. So now we are defining something which is called the total misclassification rate. So RR is the misclassification rate of a leaf R, capital. So we are summing over all the leaves. So we have the misclassification rate of each leaf multiplied or weighted by the importance of the leaf. And then we are summing up over all leaves, and this is the misclassification rate. Again, you can interpret this in terms of probabilities if you want. So you can say that this nu is the probability of ending into a given leaf, and then R is the probability of being misclassified, given that you have ended into that leaf. So somehow this row here is measuring the total probability of classifying incorrectly a point in the training set. So that's maybe a useful way of thinking. So rho T is the total probability of misclassifying. Or if you don't want to use the probability concept, you can just think that leaf containing lots of points is an important leaf, and we don't want that the important leaves are misclassifying. So therefore, you weight an important leaf's misclassification error by the importance of the leaf. So different ways of seeing, but so this is the total misclassification rate. And if you don't care about the complexity of the tree, so how large the tree is, etc. So this is a fine measure for you to describe the quality of your classification tree, obviously. But of course, this is only relative to the training data. So you don't know how well it's classifying some other data. But so if you are just testing your tree with the training data, so this rho T is a fine measure telling you how well your tree is performing as a classifier. Now we come to the question of complexity, and so as I said, if you have the maximal tree, all leaves are pure, because that's by the definition of the maximal tree. That's the case. You continue splitting until your leaves are pure, and so there's no misclassification at all in your maximal tree, and so therefore the total misclassification rate is 0. So your maximal tree is doing perfect job with the training data. Okay, so that's only with the training data. Now you have something which is called the complexity of the tree, and you can measure the complexity, let's say, by asking how many leaves do you have in your tree. So this like absolute value or size of T is by definition the number of elements in the set of leaves, or number of leaves in the tree. And obviously if you have lots of leaves, you have a complex tree, so it is a huge tree. And so we call that complexity. The measure of complexity is given simply by asking how many leaves do you have in a tree. Now we want to have a tree which is not too complex, but which still is doing a decent job with the training data, in classifying the training data. And so therefore we define this cost complexity measure for a tree by taking a linear combination of these two measures. So rho t is the misclassification rate, and then you say plus alpha, where alpha is some positive number times the complexity of the tree. And so now we use the principle that we find an optimal tree, not a maximal tree, but optimal tree, by minimizing this cost complexity function. So we are making a trade-off between the quality of the tree as a classifier with the training data, so rho, and on the other hand with the complexity of the tree. And you see immediately that this number rho here, rho alpha is strongly depending on how you choose this alpha. So if I put alpha equal to 0, then what I'm maximizing, optimizing, actually we are minimizing this quantity here. So what am I minimizing if alpha is 0? I'm minimizing the total misclassification error, and the answer then is, okay, so the maximal tree is the optimal tree. And in general, you would say that the larger the tree is, the better job it does as a classifier. While if you start increasing this alpha, so you give more and more weight to the complexity. And so when alpha gets larger and larger, you are penalizing, because you're minimizing here, you're penalizing more and more for the complexity of the tree. And at the end, when alpha goes to infinity, you decide, well, the optimal tree is the one where I only have the root element, because the weight of the misclassification is so small compared to the complexity that I decide to go for the least complex tree, which is just one single rectangle. So you see that this alpha here is crucial. It is the alpha that decides how complex trees we are going to have and how well the tree is classifying the training data. So choosing this alpha is not a trivial task, and in fact we are approaching this problem now algorithmically, so that we are choosing a sequence of possible values of alpha, and then we are choosing the alpha using, let's say, test data, which is not the training data, and we choose from the discrete values of alpha, the optimal alpha. So that's the strategy. So we need to find a way to choose some discrete values of alpha so that we can choose, among the possible values of alpha, the tree that does the best job with some independent test data that we are going to apply this classifier tree to. Okay, so how could we possibly choose a, let's say, sequence of discrete values of alpha that we are somehow controlling? So the idea here is that you start pruning the tree, and you try to make a sequence of trees which are smaller, 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 and then you check which value of alpha makes the next tree, the smaller tree, the optimal tree compared to the previous tree. And so this gives you the discrete values of alpha that you can then use to choose your classifier tree as you wish. Okay, so I'll go through this idea here step by step so that you see what the idea is. So here are the observations that I already mentioned. So alpha is 0, the maximal tree is the optimal one. And if alpha increases, you make the optimal tree simpler and simpler. And so the idea that I mentioned is that you start pruning and you make a sequence of trees which are nested, and then you choose alpha so that the tree that you're looking at is doing the optimal job. Okay, so we'll do that soon. Okay, so there are some concepts that we need to introduce. So first of all, if you have a tree T, so what is a pruned tree? Pruned tree means that you cut off a branch from your tree. Let me show you a picture. This is maybe easier to. So I'm jumping a couple of slides ahead, and so you see what a pruned tree looks like here. So here is a tree, and so this T is a tree, and so suppose I choose one of these rectangles, in this case R2, and I'm cutting off my tree at R2. And so I'm eliminating all the rectangles which are below this R2. And so then I end up into a pruned tree. So see on the right you see a pruned tree. It's a pruned version of the original tree. So pruning means that you cut at some node and you eliminate anything that is below. So that's the concept of pruned tree. And the pruning is always done at the node, so we are not cutting off one single branch. So we never do that, like we are cutting the left branch and leaving the right branch, because that is not helping us in classification. So every node needs to have left and right offspring. So therefore, the pruning is always done cutting at nodes. So when you cut a node, you are cutting all branches, whether they are on the left or on the right, below that node. And so when you do the pruning, the node at which you are pruning, which was not a leaf before, it becomes a leaf. So here's the picture. So R2 is not a leaf because it has offspring. So the leaves here are 8, 9, 10, 11, 14, or 6 also, 14, 15, and 13. So R2 is not a leaf. When I prune at R2, R2 becomes a leaf. So now it is a leaf. So that's the idea. Okay, so the selected node where you cut, it becomes a leaf because you take off both offsprings. And if you have a tree that is obtained from T by pruning, so T hat is a tree that I obtained from T by pruning, I'm using the notation that T hat is less or equal to T, so it is a subtree. So T hat is a subtree of T. So it has the same root, but some branches are missing. So that's what this notation means here. Now, we said that we are looking for the optimal tree. So we can say that given an alpha, if alpha is fixed, an optimally pruned tree is a tree which is the one for which this cost complexity function is minimum, and this optimal is calculated over all possible trees that are obtained from the original tree by pruning. So optimal tree is a subtree of the original tree. That's the first thing, and it is the subtree that which is minimizing the cost complexity function. And so now you may have several subtrees which have the same cost complexity function. And we define the smallest optimally pruned tree by saying that the smallest optimal tree is a tree which is a subtree of all possible optimally pruned trees, T prime. And there's a little bit of graph theory here, which I'm not referring to because it's not clear that you find that an optimally pruned tree exists and it's unique. You have to do a little bit of graph theory to prove this, but so I will skip that because this would lead me to a different tangent, so to speak, which I don't want to do here. So I'm just saying that one can prove that the optimally pruned tree is unique. So there is, for given alpha, you can find optimally pruned trees, and you can always find a smallest optimally pruned tree. So I should say smallest optimally pruned tree is unique. So there's a one word missing here, namely this smallest. So there is always a smallest optimally pruned tree. So this is something that I'm not going to prove here, but so that's, if you're interested, you can look at books of graph theory and in particular tree graphs, and so so the proof is there. So so how do we do this pruning in practice? So let's go through the steps. So first of all, you have a tree T, and so you choose one rectangle R bar, and so I will go through how you choose that R bar, and so let's call T prime the subtree with root R bar, and so then the pruned tree pruned at R is T minus T prime. So we are using this notation. You have the original tree and you subtract the tree that has this selected rectangle as a root. So here is the same picture again. So this is my T, the original tree. Now T prime is the tree that has this R2, which is my selected R bar, as a root. So I select one node and I look at the tree that is below that rectangle, and so therefore this selected rectangle R bar, which in this case is R2, is the root for this tree T prime. So I'm calling T prime this tree in the pink rectangle, and so then my T minus T prime is the pruned tree where I have eliminated all the offsprings of that rectangle R2. So these are the notations. T minus T prime is less or equal to T because it's a subtree, and T prime is this tree that is below my selected node R2. And so just for future, so let's look at how many leaves do we have in these two trees. So if you look at this tree on the left, you see that we have 8 leaves. 1, 2, 3, 4, 5, 6, 7, 8. So these are the leaves. And if you look at this prune tree, we have 5 leaves. 1, 2, 3, 4, 5. And if you think how you arrive to that number, you calculate how many leaves you had in your T prime tree. So we have 4 there, 1, 2, 3, 4. So we are eliminating 4 leaves. So that means that we start with 8, we eliminate 4, we arrive to number 4. But then we have to remember that this R2, which was previously not a leaf, becomes a leaf. So what I have is 8 minus 4 plus 1. So this is an important formula here. So you have number of leaves or complexity of T minus the complexity of T prime, which is the tree that you cut off, and plus 1, because the new node that was not a leaf becomes a leaf. And so this is how you get to the number 5. And so I think this is, yes, okay. So I'll go through this slide and then we can have a small break. So this is what I just said. So if you are given a tree T and you pick a rectangle, which is not one of the leaves, so R bar is not in the set of leaves of that tree. So the question is how much the complexity changes if we prune at R prime. So there are two observations. So R bar becomes a leaf. So one is added and all the leaves of T prime are removed. So now the complexity of T minus T prime, which is the prune tree, is, so this is the formula that we have to remember. It is the complexity of T minus the complexity of T prime plus 1. So this formula is important, and so this is one of the formulas that we need to bear in mind when we do the pruning. So before I go to the details of the pruning, so let's have a small break so we can continue. Let's say at 4:05. So we have like, let me check that this is my watch is running correctly. Yeah, so we have like 10 minutes break. So 5 minutes after the hour we'll continue. Okay? Okay. Thanks. Okay, so welcome back, everybody. I continue sharing my screen. Let me see. Here we go. All right, so so we were talking about. Okay, so let me see. We were talking about the complexity of a subtree. So how much complexity do you gain if you prune a tree? So this is the question. So if T is the original complexity, the new complexity, or the complexity of the smaller tree, T minus T prime is minor to the original complexity by the difference T prime minus 1. So that's how much you gain if you cut off a tree T prime. And so you see that if I cut off a tree with lots of leaves, then the gain is large. If I just cut like from a branch where you have only 2 leaves, so then the gain is just 1, but you always gain something, so that's important to know this. Okay, so now we need to do a little bit of calculations here. Oops, sorry. So suppose I have this situation, I have 3t and then I have a t prime tree. So I'll go back to this picture. So t prime is this smaller tree where I have chosen one node, in this case R2, and the tree that is growing from that root is t prime. Okay, so t prime is the tree that is below my selected node, and I'm denoting by L prime the set of leaves in that tree that I'm cutting off. Now, if you look at the cost complexity function of my original tree, so rho alpha. So first of all, I have the misclassification rate, the total misclassification rate. So I can divide it in 2 parts. So the misclassification, this first one, is the misclassification because of the leaves that belong to this T prime that I'm going to cut off. And then I have the misclassification rate of all the leaves that were left when I cut off the T prime. So I'm splitting this misclassification rate in 2 pieces, first of all. So then I'm adding and subtracting alpha times the complexity of T prime from this number. So here I'm adding it, and here I'm subtracting it. So I have not done anything. I'm just adding and subtracting the same number from the cost complexity function here. The only thing that I have done, I have divided the misclassification rate in 2 pieces. What is from L prime and what is from the left, the tree that is left when I do the pruning. Now let's look at the cost complexity function of the prune tree. So T minus T prime. So this is the tree that is left when I cut off at R bar. So first of all, there is a contribution of misclassification for the new node. So that's the first term. And there is a contribution 1 from that new node because I'm adding, remember, alpha is multiplying the number of leaves, and I'm adding 1 leaf. So I'm adding 1 alpha here. And then I have the misclassification rate of the remaining leaves, which are already in the old tree, but not this R bar, so it is here. And then I have the number of leaves that were left from the original tree when I cut off the branch. So here I have written again this cost complexity function in a slightly different order. So remember, this alpha here comes from the fact that R bar is a new leaf, and this is the contribution from the leaves that were left when I cut off the branch. So now if you compare these 2 numbers here, so they are organized in such a way that it's easy to see what the difference is. So if I take the difference between the cost complexity function of the new tree and the old tree, I see that these leaves that are common in both and their contribution to the misclassification, that cancel. Also, this alpha times t minus t bar, t prime cancels. So when I subtract these two, so what I'm left with is the misclassification rate of the new leaf, which is r bar, plus alpha. So this is the contribution for the cost complexity of the new leaf that I just created. And then I have the term, which is the cost complexity contribution of the part of the tree that is left when I cut. No, sorry, this L prime is what I'm taking off. Sorry, so this is with the minus sign. Yes, so this is what is taken off by cutting off the tree t prime. So contribution from the new leaf minus what was removed by cutting the big branch. So this is somehow understandable formula. Now, if you look at this formula here, you notice that this number here is always positive. So I'm not going into detail how you see this in looking at the formula, but let me try to explain why this is the case. So if alpha is 0, when alpha is 0, you never give any weight to the complexity of the tree. And of course, the bigger tree is doing a better job in classification than the smaller tree. And so therefore we know that for alpha equals to 0, let me see, the cost complexity function is larger for the smaller tree than for the smaller tree than for the bigger tree. So why? Because there is no cost on complexity, but there is only cost from misclassification. And the smaller tree is doing a poorer job in classification than the bigger tree. So the cost complexity of a smaller tree when alpha is 0 is larger than the cost complexity of the bigger tree. And so therefore we know that this difference here is at alpha equal to 0, it is positive or non-zero, non-negative, sorry. Now suppose you start to increase alpha. So what does it mean? It means that you start to give more and more weight to the complexity of the tree. And of course, at some point, the smaller tree wins, because the larger alpha is, the bigger the cost is for having complexity and lots of leaves. So at some point, for sure, when alpha starts to increase, you come to the point where you say, well, with this alpha, the cost complexity function of the smaller tree is smaller than with a big tree. So you start with the alpha equals 0, you know that the bigger tree is better. When alpha increases, at some point the smaller tree becomes better. And so now the question is, what is the value of alpha when the bigger tree stops being the optimal tree and the smaller tree becomes the optimal tree? So the critical value of alpha is obtained exactly when the cost complexity of the smaller tree equals the cost complexity of the larger tree. So we are solving for alpha. We are asking what alpha makes the smaller tree better than the larger tree. And so if you look at this difference, we had it here. So this is the difference. So I'm writing that this is equal to 0. And then I'm solving it for alpha. So alpha is here and alpha is there. So there are the dependency is linear. And so you realize that alpha that switches the smaller tree to be a more efficient tree than the larger tree is this alpha r bar, which is given by this ratio. So let's look at this ratio. So this is the misclassification error of the new leaf minus the misclassification error of all the leaves that were taken off, divided by t prime, which is the number of leaves in the branch that we cut off, minus 1. And so in particular, if I'm cutting off a tree which has pure leaves, so suppose I'm cutting off pure leaves. So if we go back to this picture, suppose this R8, R9, R10, and R11 are all pure leaves. So they have no misclassification error at all. So in that case, the sum of misclassification cost is 0. And so then this alpha has a particularly simple form. It is the misclassification rate of the new node divided by t prime minus 1. Okay, so here is my conclusion. So if the leaves are pure, so if RR is 0 for all leaves in the tree below where I cut, then this alpha has this very simple formula. And we use this formula, this alpha here, to generate a sequence of pruned trees. And so here is the idea. So we start with the maximal tree, and I call it T0. Okay, so I grow a tree and I go until I have the maximal tree, and I set my alpha 0 to be equal to 0. So this is the initial discrete value of alpha that I'm considering, and then I set my counter k to equal to 0, and so then I continue pruning. So I'm creating a sequence of pruned trees, tk, and I'm continuing until I have a trivial tree so that my tk is simply the root node. So I just keep cutting until I am in the situation that I only have one single rectangle, which is the original rectangle, which is the root. And so what is the procedure? So I have the tree in front of me, and so I identify all the nodes which are not leaves. And then I'm calculating for each one of those nodes this alpha, which is the critical value of alpha, for which the smaller tree starts to be a better tree. Okay, so I'm calculating these numbers. And then I'm choosing among those numbers, I'm choosing the minimum of these numbers. And so I'm calling this alpha k plus 1. And so then I'm pruning my tree at that node that corresponds to the minimum of alpha, and I denote this new tree by tk plus 1, and then I continue. So what is the idea here? So we can argue. I'm testing all the nodes which are not leaves. I'm asking, what is the alpha value that makes the smaller tree better than this tree if I cut from this node here? So I have all these alphas, and I choose the smallest possible alpha of those finite values, numbers of values of alpha. And so what I can argue is that when alpha is between the old alpha k value and the new k plus 1 value, the bigger tree that I started with is the optimal tree. While if alpha gets smaller than that value that I just found, which is the minimum, then the smaller tree is the optimal tree. And so I can argue that my alpha values are now classified in such a way that I have a piecewise constant function, and the change from one optimal tree to another is happening where my piecewise constant function is jumping. So I'm not sure if I explained this well, but I believe that it is better if I go through an example so that you see exactly what we do. So here is the algorithm. So the algorithm produces a sequence alpha k tk, so that I have these values alpha 0, alpha 1, alpha 2, etc., alpha m for some m. I don't know what this m is, but there's a finite sequence of these. And so what I have is that this tk plus 1 is always a subtree of the previous tree. So I'm creating a sequence of nested trees so that the new smaller tree is always a subtree of the bigger tree. And I'm interpreting this way that if alpha is between alpha k and alpha k plus 1, the tree tk is the optimal tree. Because if I make my alpha larger, then this tk stops being the optimal tree and tk plus 1 becomes the optimal tree. So I can divide my interval of alphas in smaller intervals, and in each interval I always know which one of those trees is the optimal tree. And when I'm moving up then I have to change the tree. So I have created values of alpha, discrete values of alpha. So now the question is, nobody told me yet how to choose this alpha. So what alpha should I use to choose the coarse complexity function? And so here's a practical rule. So you test the performance of these discrete trees with an independent set of annotated test data. So you take some test data which you did not use to construct your tree, and then you test which one of these trees in a sequence is doing the best possible work in classification. And then you choose a tree that is misclassifying least, and that's your optimal tree. So this is a little bit like we don't really know what alpha value we should use, and so we use an empirical criterion for choosing alpha. So if you are given annotated data set, what typically you have to do, you have to split your annotated data set in two, like half and half randomly, or whichever way you want. You use one half of the data to construct the tree, the maximal tree. Then you do the pruning, and then you use the second part of your data to test which one of those pruned trees is doing the best possible job in terms of misclassification. And that's your tree that you're using for classification afterwards. Okay, so this is the idea. So one half of the data for constructing, then you do pruning, and then you do testing. So there are like three phases here. And this is a rather well tested way of doing things, and so this is what we suggest here. So let's look how you do this pruning, because it's a little bit, I mean, when you see the algorithm, it kind of looks clear, but then one can also ask, did I really understand what's going on? So I go through step by step the pruning process with a tree that I suppose that I have constructed using the training set. So here is my original tree, and notice that this is a maximal tree because all the leaves are pure. So what do the numbers mean here? So I assume that I have, let's say, 100 data points at the beginning, and 60 of them is class number 1, and 40 of them are in class number 2. So my mixture of data in this case is 60-40. And then I do the optimal splitting, and I'm assuming that the optimal splitting is leading to the following situation. So 50 points went to the left offspring, and 50 went to the right offspring. And so in the left offspring, 40 of the data points are in class 1 and 10 are in class 2, whereas in the right offspring, 20 of the points are in class 1 and 30 are in the class 2. So I don't know how the data looks like. This is sort of the hypothetical situation, but I'm assuming that the first split leads to these two rectangles. Then I continue splitting, and so if I'm looking at this right component, so I'm assuming that the next split produces pure leaves, and then I stop splitting there. So my 20 points in the first class contained in R2 goes in rectangle R5, and the 30 which are in class 1 and class 2, the 30 in class 2 go to this R6. If I split the left one, I'm assuming that the next split produces one pure leaf and one mixed leaf, and then I'm splitting the mixed leaf, and then I get pure leaves. So now all the leaves are pure, and I stop splitting. So this is the maximal tree. Okay, so this is my hypothetical tree. So now I want to start pruning. So what I need to do is I need to calculate the alpha value, the critical alpha value corresponding to all nodes which are not leaves. So which are those nodes? R0, R1, R4, and R2. So those are the nodes which are not leaves, and I have to calculate the critical alpha value for those nodes. And then I'm choosing one of them which is producing the minimal critical alpha value. Okay, so let's see what the values would be. So here's my picture. So let's look at R1 for the sake of the argument. So R1 is this node here. So the splitting is 40 to 10. So what is the winning class here? The winning class is the pink class, which is called class number 1. Now, what is the importance of this leaf? So how many points do I have here? So I have 50 points here, 40 plus 10, and the original number of points is 100. So the importance of that node is 1/2, 50 over 100. So 1/2 of the original data points are in that node. So it is rather important node because it contains 1/2 of the data. What is the misclassification rate here? I have 50 points, of which 10 are misclassified. So the misclassification rate is 10 over 50. So this R1 is 1 over 5. So these are the numbers that I associate to this R1. So then, what is the critical value? Okay, so here I'm calculating. Okay, let me see. Yes, so I'm calculating the same numbers for R2. So here is my R2. So what is the winning class? The winning class is the blue class, which is 2. And so what is the misclassification? So the importance of that leaf, it is also 1/2 because 1/2 of the data points are contained in R2. So it's 1/2. And what is the misclassification rate here? 20 points are classified into the non-winning class. And so therefore the misclassification rate is 2 over 5. So pretty simple calculation, as you can see. And let's look at R4, which is here. Okay, so what is the importance of that? So first of all, the winning class is the red class, which is the first class. So 1. And what is the importance? We have 30 data points there out of 100. So the importance of that node is 30 over 100, which is 3 over 10. And then the misclassification is we are classifying this according to the winner takes all strategy to class number 1. So all the blue ones are misclassified. And so since they are 1/3 of the points, so the misclassification rate is 1/3. Okay. So we have calculated those numbers for R1, R4, and R2. We need to also check the root node because the root node may also be a winner. So let's look at the root node. Root node, it contains mostly the winner takes all principle would classify. If you would use R0 as a classifier, it will classify your point into class number 1 because there are more red points than blue points. The importance of the root is huge because all points are there. So the importance is 1. And the misclassification error is 40 over 100. So all the blue points are misclassified. And so I see that the misclassification rate is 2 over 5, which is, let's say, relatively high. Okay, so the importance is large, but the misclassification is also somewhat high. So now we go and calculate the alphas. So remember, all these nodes have only pure leaves. And so remember the pure leaves formula was that you take the importance of the node, that's the misclassification error of the node, and then you calculate how many leaves you would eliminate minus 1. So if I cut at R1, let's go back. If I cut at R1, I'm eliminating 1, 2, 3 leaves, and I'm adding 1. So 3 minus 1 is the t prime minus 1 here. So I'm calculating this alpha, and this alpha is now with the numbers that I just showed you, 1/2 times 1/5 over 2, which is 1 over 20. So then I'm calculating the same number for R2. So here I would eliminate only 2 leaves. So let's look at R2. So R2 is here. So if I take R2 and prune from here, I'm eliminating 2 leaves. So the gain in complexity is not large, it's 2 minus 1. So I'm just eliminating effectively 1 from the complexity. And the importance was 1/2, and the misclassification rate was 2 over 5, so this is 1/5. That's the critical value alpha. For R4, I get a similar value 1 over 10. And what about the root node? So the importance is 1, misclassification rate is 2 over 5. If I prune from there, I would eliminate 5 nodes, 5 leaves, and I would add 1, so I get 1 over 10. So now remember, what was the criterion? So you calculate all these alphas, and you choose the one which is smallest. And we see that this 1 over 20 is smallest. So the first pruning is done at R1. So I'm cutting from R1. And so the new tree that I get when I do the pruning is that I just remove all the offsprings of R1. And so I get this subtree. So the conclusion is that we prune at R1 are resulting in a tree T1. So why is, if you want to understand why this algorithm chose the pruning node to be R1, the reason is that R1 eliminates a lot of leaves, first of all, so it decreases the complexity of the tree quite a bit. On the other hand, the quality of the classification of R1 is not that bad. So the misclassification rate of R1 is not large because it is almost a pure leaf, but not quite. So there is like 80% of points are in one class and 20 in the other. So R1 somehow intuitively is a very natural place to prune because first of all, you are not decreasing so much the the misclassification of this tree, but on the other hand, you decrease a lot the complexity when you prune from there. So that's where we got. And so this is my first tree. And so remember the first value alpha is 1/20. Alpha 1 is 1/20. So now we start and we continue. So now we ask where do we prune next? There are only two candidates. There is R2 and there is R0. Well, the numbers for R2 we already calculated because we didn't change this branch of the tree. So I know already what the importance of R2 is. I also know what the misclassification error of the leaves or this R2 is because the leaves are pure. So I have calculated it. I have to recalculate the values for R0. Why? Because I changed the leaves under R0. So remember, let's go back and see this formula here that I had. Here, you see this alpha formula. So this alpha formula contains a term that is referring to all leaves which are under the rectangle where I cut. Now I have changed the leaves of R0 because previously the leaves were these pure leaves. These are leaves corresponding to R0. When I have pruned, I have only 3 leaves and these are not the same leaves. And so therefore I need to recalculate the critical alpha for R0. And so let's see what this alpha 0 is. So importance does misclassification for R0 is 2/5. But now I have one pure leaf, a non-pure leaf, a mixed leaf, which is R1. So I need to take the importance of this leaf and its misclassification error, and I have to subtract that. So that's the only contribution which produces misclassification among the leaves under R0. So therefore I have to calculate this. Now the number of leaves that I would eliminate if I eliminate if I cut from R0 is 1, 2, 3. So I'm cutting away 3 leaves. So I get 3 minus 1 in the denominator. So calculating this number, I see that this is 3/20. Now 3/20 is less than 1/5 that was this alpha, critical alpha for R2. So what does it mean? It means that that I need to calculate, I need to cut from R0. So my next tree is going to be the trivial tree. So T2 is going to be R0. And so we see that if I choose alpha to be 3/20, then I get a more efficient classification tree than what I would get, which is this one, if I would cut from R2. So this tree that you see here, which is not one of the trees that I want, is a tree which has more complexity than the tree that I get if I just prune by R0. But the classification quality of this tree is not justifying the use of this tree. So in this particular computed example, I have obtained 3 trees. My original tree, which is this one, That's T0. Then I get T1, it is here. And then I get T2, which is only the root node. And that's it. And so then which one should I use for classification? I take the test data, and then I'm testing which one of these trees is doing the best job. And that's the tree that I'm going to select. So I hope this example showed you how you work out this pruning process. The implementation of the pruning process is, of course, a little bit a bookkeeping problem because there is a lot of indices that you need to keep. And I'm not going too much into that detail here. In the book, there's a detailed description of how you do the implementation using adjacency matrices and next generation matrices, etc. So it's rather technical. It's not difficult. It's more like just bookkeeping. So rather than that, I'm going to show you an example, and this is a rather simple data set. However, this is a rather famous data set too. So it's called the IRIS data. And why is this data so famous? So this data set was used by Ronald Fisher in his 1936 in one of his famous papers from 36, where he I forget what that paper was about. It was not about trees, but it was something else. So he chose what he calls the Anderson's data set. So the data goes back to botanist Edgar Anderson in 35. It is a very simple data set. So the botanist was looking at 3 flower species, which were all iris flowers: Iris setosa, Iris virginica, and Iris versicolor. And I show you here the picture. So these are the irises. So I think this is from Wikipedia. So what Anderson was measuring was the length and width of the sepal and petal leaves. So petal leaves are these long ones. So you measure the length of the petal leaf and the width of it. I believe it's from here. And then you have the sepal leaves, and you measure the length and the width. So there are 4 numbers associated to each one of these flowers. And so Anderson was looking at, a mechanic, quick way of separating between these 3 iris species. So your data consists of 4 numbers, and there are 4 attributes. 4 attributes: petal length and width, sepal length and width. And there were, in the Anderson dataset, there were 50 readings for each species. So you have 3 classes and 50 from each class. So you have 150 data points, and the number of attributes is 4. And so this dataset you find anywhere. So you go to internet and you type iris data, and you will certainly see this dataset. And in order to test the tree algorithm, I'm first splitting my data into classes: the training data and the test data. So the training data is used to build or grow the tree. Then I'm doing pruning, and then I'm choosing the tree by using the test set. So 1/2 of the data is used from testing, and 1/2 is used for training. So I have now training set and test set, and there is a typo here. So the size is 3 times 75. So I have 3 classes. So I have sorry. It is correct. I have 25 data points for training and 25 for testing from each species, and this 4 is referring to the number of attributes. So I have 25 from each species. So that is correct. So I misinterpreted my own writing. Okay, so 4 by 75 is the matrix that you use for growing the tree. Okay. So here are the protagonists. And so what I have plotted here, it turns out that when I do the splitting, The first splits, the 1, 2, 3, I think four first splits, they are all related to attributes x3 and x4. So the attributes x3 and x4 are maybe the best separating attributes, petal length and petal width. So those are the most significant attributes here. And so therefore it is possible for me to visualize this data by showing how this algorithm is working. So this is a two-dimensional projection of the data, and the projection is in the x3, x4 plane. So when I find the optimal split, it turns out that the optimal split is this one here. So it is separating completely the red dots, and I believe that's maybe Virginica. Let me see. It's no, it's versicolor, I believe. So the last one, I believe that the last one is easiest to separate, I believe, if I remember correctly. So you see that one of the groups anyway is separated completely. So when I split my data along this line here, I create one pure leaf already, and I have a mixed leaf here. So then I continue, and so the next split is again in this x3, x4 plane, and it takes place here. So you see that there's a little bit of misclassification here, not much, but so one green point is misclassified to among these blue points, and one blue point is misclassified or classified, differently in R5. So this is already a rather good classifier. So, but we continue until we have pure leaves, and so the next split is splitting. So this is the third one. So this is splitting R4 into 2. So I get R6 and R7. And so this is separating 1 point from this group of points. And then the last split here is just cutting this R5 in 2, so R6 to R9. And then the splitting continues. The next split is not going to be in this plane, so I'm not showing that. But so I just show you first 4 splits here. And so now you see what I meant when I said that the classifier is sort of prone to misclassification. So look at this R6 and R7. So what the numbers are that we are looking at here is the petal length and petal width. And so these are numbers that the botanist Anderson was measuring with his measuring tape. So suppose he made a small mistake in the measurement, or the leaf was a little bit irregular or something like that. So then this green point could easily be on the other side of any one of these separation lines. And so the third split here is based only on one single data point. So how I divided R4 into depended only on one single data point. But that single data point could be mismeasurement. So there could be a lot of noise in that. And so you see that this tree is becoming sensitive to rather marginal number of data points. And so therefore, one has to be careful when one talks about the performance of the tree, because the tree is always first tested with the training data. And so therefore, we need to do the testing with independent test data. Okay, so but this is how it looks like. Now I go and I draw a tree, so the tree looks like this. So the original tree is R1, then I split in R2, R3, and so this is the pure leaf, which contains only the red dots, so I'm not going to split it anymore. And so then the splitting continues with the ones where I have green and blue dots, and so this is the structure of the maximal tree that I get, and so then I have pure leaves. And so then I start pruning. So I'm asking which one of these nodes, R1, R3, R4, or R5. So those are the nodes which are not leaves. So if I prune at one of those nodes, which one takes me to to the tree that is minimizing the cost complexity function. And so if I cut at R5, I get this pink large box, because what I'm cutting off is the nodes which are outside this pink box. If I'm cutting further from R4, then I'm cutting away these 6 and 7. So this is how my trees are going to look like. So I have already indicated here what the pruning process is going to give me. So the first pruning is going to be taking place from R5. The next pruning will be taken place at R4, and the third pruning is going to be at R1. So these are the minimal alpha values, and so here are my alpha values. So first I'm testing where to cut. What are the possibilities? 1, 3, 4, 5, or 8. So those are the non-leaves. 1, 3, 4, 5, 8. So 1, 3, 4, 5, 8. So these are the non-leaves. I calculate what the critical alpha for those nodes is. And the values are 1.01, 0.133, 0.125, 0.04, 0.02, 0.05. So comparing these numbers, I see that if I cut at 5, I get the smallest alpha. So since this is the smallest alpha, I cut at 5. So now I have the tree where I have left out R8, R6, R10, and R11. So what are the non-leaf nodes here? They are R4, R3, R1, 1, 3, 4. So I calculated the critical alphas for those nodes, and I realized that 4 is the smallest of them. So the next cut is at node 4. So I'm cutting from here. So I'm left with the tree which is inside this box here. So what are the non-leaves here? 1 and 3. Okay, so I take 1 and 3. I'm calculating the critical alphas, and I realize that the smallest alpha corresponds to the root node. And that's the end of the story. So I have created 3 trees, and they correspond to alpha values 0.02, 0.04, 0.32. Now I take the second half of my data, which is called the test data. And then I start testing which one of these 3 trees I should use as a classifier. And so here is my so-called confusion matrix. So what is a confusion matrix? In the rows, I'm indicating what the true class is. And in the columns, I'm indicating in which class each data point will be classified. So obviously, tree 1 is classifying every class 1 data points into the correct class. Of the 25 points which are in class 2, 23 are classified correctly and 2 are classified incorrectly to class number 3. Similarly, of the class 3, 23 are classified correctly and 2 are classified incorrectly. So when I'm looking at this confusion matrix, I realize that the classification rate, so the percentage of points which are classified correctly, is I take the sum of the diagonals and I divide by 75, which is the total number of points. So those are the points that were classified correctly. And I realized that 94.7% of the points were classified correctly if I use tree number 1. Then I take the tree number 2, which is the tree that was slightly pruned, and I do the same calculation. I realize that first class and second class are completely classified correctly. The third class, almost 23%, 23 points are classified correctly, and 2 are classified into the second class, which is the incorrect class. And so now I see that the classification rate is 97.3. Then I go to tree number three, and I see that the classification rate is again the same as it was in the first tree. And the last tree, it is 28.8. So here I'm using only the root, and so you might wonder why I didn't get 1/3, because originally in the root I have 1/3, 1/3, 1/3 in the in the different classes. So remember, when we do the classification using the winner takes all principle. So if you have a rectangle where you have 2 or more classes which are equally well represented, so then we are flipping the coin and we are just picking randomly the classification. So this 28.8 is just a result of a random classification. So it optimally it should be 1/3, because that's the probability of classifying correctly. But so in this case it was slightly less, and so you get all these random numbers, and you see that this is really a tree that is worth nothing here. So we have to choose between these trees, and since the success rate in tree number 2 was the highest, that's the tree that's the winner. And so tree number 2 is this tree here where I have left out R8, R9. Let's see if I see it here. R8, R9. So look at this this last split here. So the last split, hardly improves the classification properties of the tree, because there's just one point which is on the other side of this blue point, but it increases the complexity because I'm still splitting this R8 to further nodes 10 and 11. So you see that the R6 leaf here, it is almost a useless leaf, and it adds a lot of complexity. And so therefore it's very natural that R5 is the one where you cut. But you don't have to look at this picture, you just calculate these alphas and you see which one is the way to cut, and then you test it with the test data and you see that this is the most efficient tree. Okay, so that's more or less how these tree algorithms look like. So now let me comment on an algorithm which is really let's say a popular algorithm, and it has been tested and its performance is rather good, and it's called random forests. So suppose you have a lot of data points. So remember, when we are doing this optimal splitting, the algorithm, because it is an exhaustive search algorithm, can become really heavy. So you may not want to use all the data points to do the tree growth. And so a very natural idea is that you do subsampling. So you take your data points and then you randomly sample your data points, and you use a smaller subsample of the data to grow a tree. But on the other hand, you don't want to waste your data, so you don't want to throw away the data either. So what you can do is you pick randomly a subsample of the data and you grow a tree, and then you prune it. Then you do another subsampling of the data and you grow another tree and you prune it, etc. And so in this way you are growing a number of trees. They are random trees because your sampling is random. So they are slightly different from each other, but they are basically using the same amount of data because you're picking a certain number of data points from your original big data set. So what you get by this is a forest. So, and this is called a random forest. So instead of growing a huge tree that is using a massive amount of data, you decide, I'm going to grow 150 trees which are smaller in size, and they are using just a subsample of the data which I'm doing. I'm selecting randomly. So you're sampling randomly your data, and then you get all these trees, and they are slightly different from each other, and that's called a random forest. Now, how do you test your random forest? Which tree from the random forest you take? Well, you keep all of them. In the random forest algorithm, you keep all of them, and you when a new data point comes, you present the data to all of the random trees, and you let all the random trees to classify the data point. Once they have classified, then you let your random trees to vote, and you say that the maximum maximum principle, or the majority vote principle, is deciding what your final classification is. And so this way, you are using all the data because you are doing this random sampling or bootstrapping, whatever you want to call it. And so then you grow those trees, and they are relatively simple trees because your data that you use for growing is not that large, and they are sort of representing well the data, but they're all representing in a random way. So if there is a little bit of noise in some of the data points, you can hope that this noise is canceling out. So if you have one tree that is systematically classifying incorrectly one class of data points, you may have 5 other trees which are not prone to that particular measurement error, and so they are compensating. And so it turns out that this random forest algorithm is performing really well in the sense that it really makes the most of the large data, and it also sort of cancels out the possible misclassifications due to the noise in the data. Okay, so today I will stop here with this slide. I have another meeting in 2 minutes, so if you don't mind, I stop a few minutes earlier, and so I'm going to continue with the regression tree and the application to images on Thursday. And so, time permitting, I may also be talking a little bit about page ranking, which is one of the algorithms that I didn't actually list in the possible topics of this course, but since I probably have some more time, I will go through briefly the page ranking algorithm. Also, I'm trying to produce I have already promised to do it over the weekend, the problems that you are asked to solve to pass this course. Now the semester is over here, so I have a little bit more time, and I will try to do it today or tomorrow. So, okay, so we'll see you on Thursday, and thanks everybody for joining today.
Bye.
Bye.